Hello everyone. I am Dr. Fatima Shahana, Assistant Professor, Department of Chemistry PG, Sadakatullah Upper College, Tirunelveli. Have you ever wondered about those highly reactive species that play a vital role in both chemistry and biology? Yes, we are talking about free radicals. In this video, we will explore how these fascinating species are generated, detected, their stability factor, and reactions they undergo. Free radicals. Free radicals are chemical species that contain an unpaired electron in their outermost shell. This makes them highly reactive and often short lived. The unpaired electron is represented by a dot. Some examples for the free radicals are 2266 tetramethylpiperidinoxine radical, phenylalanine radical, 1,1-diphenyl 2-picryl hydrazine radical. Generation of free radical. Free radicals are generated through several mechanisms. The most important factors responsible for the formation of the free radicals are homolytic cleavage. When a covalent bond breaks evenly, each fragment retains one electron. The first reaction for the formation of the free radicals are thermal cleavage. Free radical may be generated by thermal cleavage. In the gaseous phase, some molecules break down at high temperature. When the molecule contains bonds with 20 to 40 kilocalories per mole of energy, cleavage can be caused in the liquid phase. For example, the thermal cleavage of the benzoyl peroxide yields phenyl free radical. Photochemical cleavage. The energy of light of 600 to 300 nanometer is 48 to 96 kilocalories per mole, which is of the order of magnitude of covalent bond energies. Certain molecules undergo homolytic fission in the presence of the light of that particular wavelength. For example, the photochemical cleavage of acetone results into the formation of methyl free radical. Decomposition reaction. At times, a radical molecule may undergo decomposition to form another free radical. For example, decomposition of benzoyl radical gives phenyl radical and carbon dioxide. Detection of free radical. Free radical can be detected by ESR spectrometer and spin trapping techniques. The most common method is electron spin resonance spectroscopy, which identifies unpaired electrons by their magnetic properties. Another technique is spin trapping, where a radical reacts with a spin trap molecule to form a stable compound which can be detected and analyzed. Stability of free radical. The various factors responsible for the stability of the free radicals are inductive effect, hyperconjugative effect, resonance effect. Inductive effect. The stability of a free radical increases with the number of alkyl group attached to the carbon center. This is attributed to the electron donating inductive effect of alkyl group, which helps to reduce the electron deficiency of the radical. The bond dissociation energy of CH bonds in methane, ethane and other alkane provide evidence for this phenomenon, demonstrating that replacing 1, 2 or 3 hydrogen atom in the methyl radical with alkyl group enhances the stability of the radical. For example, the bond dissociation energy of ethane is 98 kilocalories per mole, which is less than that of the methane, which is 105 kilocalories per mole. Thus, the stability of the free radicals or tertiary radical is more stable than secondary, which is more stable than primary, which is more stable than methyl radical. Hyperconjugative effect. The hyperconjugative effect also contributes to the stability of the free radical, similar to its role in stabilizing carbocations. The stability of the alkyl free radical follows the order tertiary, greater than secondary, which is greater than primary, and which is greater than methyl radical. This trend can be explained by hyperconjugation, where the unpaired electron in a radical is delocalized onto the beta hydrogen. This delocalization imparts additional stability to the radical. For example, the tertiary butyl radical is more stable than secondary butyl radical, which is in turn more stable than N-butyl radical. The tertiary butyl radical benefits from 3-methyl group or 9 beta hydrogen, resulting in the 9 hyperconjugative structure. In contrast, the secondary butyl radical has 6 and the N-butyl radical has 3 hyperconjugative structure. A higher number of hyperconjugative structure corresponds to the greater radical stability. The stability order for the free radical is tertiary radical, which is greater than that of the secondary, which is greater than primary, which is greater than methyl radical. Resonance effect. Free radicals with a carbon center conjugated to a double bond experience stabilization due to the resonance effect. This stabilization is particularly notable in allyl radical and benzyl radicals, which can be effectively explained through resonance structure. As a result, allyl and benzyl radicals are significantly more stable than alkyl radical. However, despite their enhanced stability, they still exhibit only a transient existence under normal condition. Reaction of free radicals. The free radical reactions involves 3 main steps. The first step is the initiation step, next is a chain propagation step, and then next is a chain termination step. Chain initiation step. In this step, free radicals required for the reaction are generated in situ by irradiation or heating of the reagent or by carrying out the reaction in the presence of an initiator like peroxides. The process is always endothermic. The first step is initiation, which involves bond cleavage. Here the chlorine molecules in the presence of a heat or light undergoes cleavage to form a chlorine radical. The next step is a chain propagation step. In this step, the highly reactive chlorine radicals with unpaired electron reacts further. They are electrophilic, thus each seeks an electron to complete its unfilled shell of electrons. In a reaction with methane, a chlorine atom readily removes a hydrogen from the methane. Free radical chain reaction work best when all propagation steps are exothermic. Here, the chlorine radical reacts with the methane to form methyl radical and hydrochloric acid, and again the methyl radical reacts with the chlorine to form methyl chloride and chlorine radical. Chain termination step. The final step is chain termination, in which two reactive radicals combines together. Methyl radical combines with chlorine radical to form methyl chloride, and methyl radical again combined with the methyl radical to form ethane. Chlorine radical again combined with the chlorine radical to form a chlorine molecule. Free radicals are powerful and versatile species. Understanding their generation, detection, stability, and reaction help us unlock their potential while mitigating their risk. Thank you.